Hi everyone, welcome to the next video in our week 1 series on time series graphs. A time series graph is a graph used for quantitative paired data sets. So the last two videos we talked about histograms and frequency polygons where we had one variable. We were looking just at the number of books or the age of US presidents. Now we're looking at data that's paired. Specifically, we're looking at paired data where one of the sets of data is time. And the x-axis in these graphs is always used to plot that measurement of time. If you've taken a science class, particularly a physical science class recently, you've probably seen that. I know in physics, position versus time, velocity versus time, acceleration versus time. All of those graphs have time on the x-axis. Time series graphs will look almost identical to line graphs. They're going to be constructed in a very similar way. The only difference is in this case, the x-axis has to be time. So we've got an example here of a time series graph. It is sales in billions of dollars plotted as a function of time, specifically in months. So we can see we started in March of some arbitrary year, and we're counting by months. So April, May, June, July, August, September, October, November, December, and then here is January of the next year, and we keep going February, March, and then the process starts over again. This graph is nice because while we see fluctuations on the small scale, looking at the graph as a whole, we clearly see that that graph is increasing. So time series graphs show us, in instances like this, long-term behavior of a variable over time, which can indicate important patterns about the natural world and about man-made systems that we are interested in. So we're going to do an example. The data on the following slide shows the annual consumer price index each month for 10 years. Construct a time series graph for the annual consumer price index data only. So before I show you the data, and this is how it appears in your textbook, you'll notice that that last sentence says construct a time series graph for the annual consumer price index data only. So they've told us that my graph is going to be time versus annual data. So when I see this big, scary data table, and I look at that top row, I see January, February, March, April, May, blah, blah, blah. But I wasn't asked about individual months. I was asked about annual data. So even though they've given me a whole lot of information, the problem told me focus on time, which is my first column, versus annual consumer price index, which is my last column. So what we're going to do is we're going to simplify this picture down, and I'm going to get rid of all that data in the middle that I don't need. And that's going to make this a lot less intimidating and difficult to interpret. So we want year, we want annual, everything else can go. So here's our simplified table. We can see the years 2003 to 2012, try that again, and the annual consumer price index starting at 184 and ending at 229.6. So to draw a time series graph, we need to start with our axes, and we know that we want that time measurement, this time in years, on the x-axis. That means that our annual is going to be on the y-axis. And looking at that data, my smallest number is 184. My biggest number is 229 point something. So what I tend to do is I tend to round that smallest down to the nearest multiple of 10 or multiple of 5. And same thing for the upper bound. I'm going to round it up to the nearest multiple of 10 or 5 so that I can make the divisions on my graph nice and pretty. Something easy to count by because mathematicians are lazy. So I'm going to round that 184 down to 180 and that 229 up to 130 to scale my y-axis. So here's the axis unscaled. I've got my years on the x, annual consumer price index on the y. And looking at that biggest and smallest, you can see that my smallest is 180, and then it goes up to 225. The edge of this axis would then be 130. So that 229.6 is just going to fit. Ideally, this line would go up a little bit higher and we can squeeze that 230 in here. I was having issues with my computer and getting my pictures to cooperate. So this was the best I could do on short notice, and I apologize. You'll also notice on the x-axis for time, I've written those years vertically instead of horizontally, because if we write them horizontally, they tend to bleed into each other. So even though it's vertical text, it's actually easier to interpret this way than it would be written horizontally. So it is okay to tilt the text so that it fits on your graph in a neater way that makes it more clear and less difficult to separate categories and data points. From here, we're just plotting data points. So 2003, 184. So that's somewhere over here. 2004 and 188.9. That's almost 190. 2005 and 195.3. So about here-ish. 2006 and 201.6. So somewhere between 200 and 205. 2007 and 207.3, so a little bigger than 205. 2018 and 215. And then I'm going to plot those last three rapid fire. And then you can see 2012 is just right at the edge of that graph, right below where 230 would be. Just like our frequency polygons, we should connect those points with straight lines so that we can see those patterns in our data points clearly. And just like that last graph, that sample graph we looked at, there is a very clear increase of the annual consumer price index over time. It is, even with that small blip between 2008 2009, we see continued increase. At this point, a statistician would kind of ask ourselves what happened in 2008. And I'm assuming you were all alive, though you may not be old enough to remember that was when we had that big housing bubble burst and the economy tanked. So seeing a drop there in our graph is not surprising, because when the economy is in distress, we don't expect that our annual consumer price index is going to be very high. We expect to see that drop. Okay, so time for you to try it. We've got a table on the right that represents CO2 emissions. It's pulled from www.worldbank.org. And you're asked to use that table to construct a time series graph for carbon dioxide emissions for the U.S. So much like last time, you're given extraneous information in your table that you don't need. So make sure that you think clearly about which columns you need from this table. And I'll also give you a hint. You can turn this data into millions as opposed to counting in ones, and that might make this easier. Take a few minutes, pause the video, and try and sketch that out really quick on a piece of scratch paper, and then we'll take a look at the solution together. Okay, so I know that I'm only focused on the US, so I want that first column of time values for years, and I want that last column for the US. So I'm going to pull that into a new table without all that extraneous. And then all I did was type this data table into Google Sheets, highlight it, and ask Google to make a chart. And this is what it gave me. I did play a little bit with the values on the axis. There's a video on how to do that on that Google Sheets video links in Canvas. Sorry, lost my train of thought there. I gave you a hint on that last slide, which is you could take these really big numbers and plot them as millions instead of counting by ones. And I actually did that. And you'll notice the shape of that graph did not change. That graph has the exact same shape as the previous graph, but now the numbers on that y-axis are significantly less intimidating. So all I did, going back to that last slide, is I took these values, and I know that that millions place is where that comma is, so I'm going to plop a decimal there. So 5.681 something something million. And then I rounded to 2 decimal places. So that 5.681 blah, blah, blah became 5.68 million. 5.79 blah, blah, blah became 5.79 million. Oops, wrong direction. And that's where these values came from. It's generally okay to do that when your numbers are really big, because the numbers that I'm eliminating are in the thousands place and less. And when we're talking about millions, the thousands place is tiny, right? If you have millions and millions of dollars in the bank, you are not going to miss $1,000 like you and I would. So in that instance where you've got really big numbers, it is okay to truncate and round and count by something bigger than 1. Okay, if you have questions on how to build these time series graphs or about anything else from this week 1 series, feel free to get in touch with me via email or text message, or drop by office hours on Thursday, and I'll see you in the next video.